Square of these guys is 1, these guys here are 3, and the same for the column, right? Any question about that? 9 components, 9 different components. It's not a symmetric matrix. 9 different components subject to 6 constraints. Was a question?
Is there a reason why you were using the big bracket and the like
This?
Yeah,
because this is a matrix.
Okay, and as a
Curly bracket?
yeah, curly bracket, because it's already a vector. Why do you still need that?
Okay, this is a good point. This is a good point. Yeah. If it's a vector, actually, I'll write it like this. Maybe A is a vector, right? So it's maybe 3b1, 4b2, and 6b3. I'll write A as 3, 4, and 6. Okay? But this is not a vector. This curly bracket B is not a vector. It's a collection of the unit vectors. And this is important to distinct. B is B1, B2, B3. Here, I extract the components in this form. This is just a notation. But I like this distinction because it will matter in a minute. At any rate, RU, as you know, is a matrix. This guy is a collection of the unit vectors. This is how we relate the body frame to the inner frame. So if we were asking about how we're going to represent the angular position of my body, well, I'm going to represent it intrinsically by the rotation matrix. If I have the rotation matrix at any time, I'm done, right? Because I can relate the body frame to the inertial frame. So the question now is that, well, how can I integrate omega to get the rotation matrix, right? What is the proper way of doing it? This is what we mean by rigid body kinematics. Any question about that? So let's do it from here. Let's differentiate this equation. So B dot equals, can you differentiate this equation please? It's something times n frame. N frame is fixed by definition, so this is simply R dot in the n frame, correct? And what about the n frame? Can you replace n in terms of B again? Yeah, the second line is R transpose in the B frame. So I managed to write the right hand side as something in the B frame. I want to write this guy as something in the B frame. What's B dot? Well, B is B1, B2, B3. Okay? So what is the d by dt for each component? What's the d by dt for B1, for example? Can you tell me what is the d by dt for B1? What's that? No, from basic definition. What's B1 dot? B1 is what? First of all, B1 is a unit vector, right? And simply is rotating for sure. So what is its d by dt? Exactly. The magnitude doesn't change, but it rotates, so it's omega cross B1, correct? And the same for B2, exact same equation. B3, exact same equation. If you collect these three identities, you will get, of course, omega cross the collection, right? Any question about that? Any question? Okay, I have the right hand side as a matrix times the collection of these B's, and I want to please write the left hand side as a matrix times the collection of these B's. This is not a matrix multiplication, this is vector multiplication, right? It's cross product. So I need to turn it into a matrix multiplication, and we know how to do that if I have a simple vector, right? If I have vector A is 3, 4, and 6, so omega cross A is simply omega tilde times the components, right? But in fact, if you want omega cross the collection of the vectors, it's it's actually the negative omega tilde times the collection of the vectors. And you can check it. You can check it step by step. It's not obvious how to do it, but go and check it step by step. Do it one at a time. Omega cross B1, what do you get? Omega cross B2, omega cross B3, then try to collect the three relations into one relation like this. You will get it exactly the same. It's a little bit confusing, but it's very doable. Any question? Any question, please? Okay, so actually I'm going to write this as negative omega tilde as B. So, well, don't confuse yourself. This is a cross product, do it the way you like, okay? But at the end of the day, please write it as a matrix times the collection of B's, because I want to equate these two. Okay? If you do it like this, the only way to do it is omega tilde times the B's. And now you can get the identity. What is the identity? What's the equation that we can get out of this box? What's the equation? This guy equals that guy, right? And I can multiply by R from this side to get R dot. So R dot, which is dr by dt, equals. Gonna multiply by R from the right. Why? Because R transpose R is identity, so I got rid of this. Multiply by R from here, so I'll get negative omega tilde times R, and this is what do we mean by rigid body kinematics. Given omegas and the initial attitude R's, angles, I give you how R will evolve with time. Okay? Any question about that? This is what we call actually kinematic differential equation. I'll show you in a minute how to apply it. Any question? Please. Yes, Andrew?
Can you just explain how you went from how you got R dot?
Oh yeah, sure. Yeah, this is easy. Let's see. What you get from this, straightforward. I get omega tilde, or let's try to write this. I get R dot times R equal negative omega tilde, correct? Okay? This is R transpose. And I want to get rid of this guy. So it's as if I want to multiply by its inverse from the right. What is the inverse of this guy? It's just R. So multiply by R here, this will go away, and you'll have R here, which is this equation. Any question? Okay, let's see how to apply this equation. This is straightforward, but I'll show it to you, just in case you don't know how to apply it. So this is d by dt for R. R is cosine of 9 angles. Cosine alpha 1, equals negative omega tilde, the skew symmetric matrix associated with the 3 omega components. 0, 0, 0, it's always like this, right? Negative omega 3, omega 2, negative omega 1. It's always like this, right? So I'm given omega 1, omega 2, omega 3. How did you get your omega 1, omega 2, omega 3 in a real application? Well, I got the omega 1, omega 2, omega 3 by integrating omega 1 dot, omega 2 dot, omega 3 dot. And how did you get these guys? From Euler's equation. Okay? This is in a real application. Of course, in a homework problem, you'll readily be given omega 1, omega 2, omega 3. Negative omega tilde times R, so I'm going to multiply this guy by R, which is cosine alpha 1, 1, cosine alpha 1, 2, and so on. So, cosine alpha 2, 1, cosine alpha 3, 1, and so on. Okay? And we equate, I have here on the left-hand side, I have a matrix, so 9 elements. When you multiply these two guys, you get also 9 elements. We equate it element by element. So let's equate the first element. 1, 1. From here, it's simply d by dt for this quantity. This is a function of time, remember? So d by dt for this quantity is cosine alpha, I'll get negative sine alpha, and it's alpha 1, 1 dot equals. On the right hand side, let's multiply first row by the first column to get the 1, 1 element. So I will immediately, and there's negative here, I will immediately get omega 3 cosine alpha 2, 1 negative omega 2 cosine alpha 3, 1. And this is the first differential equation out of 9 differential equations you can get, right? This equation gives you how alpha 1, 1 will evolve with time, okay? Will give you how alpha 1, 1 will evolve with time. So given omegas as inputs, you can integrate this equation. It's nonlinear. I mean, no need to integrate it by hand. You can give it to MATLAB. And you can see that the evolution of alpha 1, 1 depends on alpha 1, 1 and also other alphas. So they are you have to solve them simultaneously, the 9 equations. 9 differential equations subject to 6 constraints. So it's pretty complicated, right? Yeah, this actually is not the way to do it. To study rigid body, rigid body kinematics, but this is the straightforward approach. This is to understand what is the intrinsic description of a rigid body attitude. It's simply the rotation matrix. How the rotation matrix evolves with time due to given angular velocity. Here is the kinematic differential equation.